So good afternoon. That's the last of the few talks we had with Gwen and Seb during this workshop. To finish with Suz, we could talk about the Ebola outbreak and in particular the impact that dynamical modeling had during this outbreak. There was a lot of work in modeling because there was a lot of question. Ebola was the first time that it was spreading so fast. So there was a lot of question, interesting modelers with potential application for the response. I probably won't have time to go through all my slides. As I said, I have too many. But I will also take the opportunity to do a little bit of a recap. So to try to put in perspective in a few slides what the students learned during our lab sessions. But I will introduce this a bit later. Just to start maybe about Ebola, it's good to remind us that a year ago the situation was this one, and so it was around the time when just after the first case was imported in the United States. And yesterday there was a talk about change in behavior and awareness. And clearly these kind of headlines can have a huge impact, not only on the public, but also on the government. And the situation a year ago was, we was there. So that's the Ebola outbreak in West Africa. So that's a time series. So that's the weekly number of new cases across time. And you see that we were at the middle of the peak of the epidemic. And it increased quickly and decreased quickly after that. And now we are here. We are almost there. So that was the Ebola outbreak. And actually, when we look back in time, the first time the first case was noticed and confirmed was on the 22nd of March 2014. There was already like around 70 cases infected by Ebola. And that's when WHO officially declared the outbreak. You see how different are these two, you never expected maybe to see that. If I zoom in a little bit on this first part of the outbreak, you see that actually the first case was recorded at the end of 2013, and that it took almost 3 months before the outbreaks was actually declared. So that's 3 months. That can be quite long. Actually, for this current outbreak, that was too long because it allowed the disease to spread very quickly across the region. And so it tells you that most of the time, the first case you observe is not, it's probably far from being the index case. So that's where the quality of the color is not that great, but that's where the first case originated. That's the village of Meliandou, and it's a typical rural village in the forest. And it's located here at the border of Guinea, Sierra Leone, and Liberia. And if we compare this to the geographical localization of the previous outbreaks that are represented by these red dots, we see that there is a big shift in the area. We are quite far from the traditional region of Ebola outbreaks, mainly Democratic Republic of Congo and Gabon. And now if I look at all these outbreaks and I put them on a timeline and I look at the size of all these outbreaks, which correspond to the size of the dots here. So here you see the first time that the first outbreak reported. This was in 1976. There was 2 epidemics, one in Sudan, one in DRC. And then we had to wait quite a bit of time before to see the epidemic being more frequent by around the mid-90s. And so since the 90s, we can see recurrent outbreaks, but all the times they are quite small. They infect a few hundreds of people. Obviously, the one here was not only in a different part of Africa, but in terms of size, it has nothing to do with what we have seen before. Nonetheless, the fact that we already knew, we already had a few outbreaks, we had some knowledge of the Ebola. It was not totally an unknown disease. And there were a few facts I'd like to share with you that we knew. First thing is that Ebola is in the forest. It's a virus that is in the forest. There is animal reservoir. And time to time, it passes from the animal to the human. For instance, when there is a big suspicion on food bat that may be the natural reservoir. And when people eat food bat, well, they can get infected. Delayed diagnosis is also a feature of Ebola outbreaks. I just showed you before that it took 3 months before the outbreak was declared. So clearly, this is good for Ebola, for the virus to spread. People get infected by Ebola, and then they tend to try to seek healthcare. So what they do, because they live in rural areas, they have to travel to cities or to the next big village. So they take cars, they travel by road, so that's allowed the virus to spread quite quickly through the roads. When these people arrive in hospital, usually the hospital is not prepared to receive an Ebola patient. So the problem is that many healthcare workers are going to be infected, or like the guy might infect other patients also. So that leads also to some kind of super spreading events, typical of Ebola outbreak. It's quite common that one guy might infect like 20 or 30 other people. The problem is that these communities, they live quite isolated, and in countries, for instance, like the Sierra Leone or Liberia, where there's a lot of for a long time there was a civil war, and so this community, for instance, are not so keen into external interventions, and there are a lot of distrust toward Occidental communities, but also towards their own government. So that makes the response very difficult. And also, Ebola spread very quickly as people don't want to believe in it, or don't think that there is good way to control. Nonetheless, we know that to control all the Ebola outbreaks in the past, 3 control measures were really efficient, and that's how all these outbreaks were controlled in the past. The first one is the isolation of new suspect cases, so they don't pass the disease if they got confirmed. The safe burials of dead bodies. Dead bodies are really contagious, and the traditional funeral ceremony involves a lot of touching the bodies, so that leads also to some super spreading event. So safe burial is really important. And finally, the contact tracing of people at risk. The fact that there is quite a long incubation period for Ebola, around 10 days. If you manage to keep track of all the contacts of a confirmed cases early enough, you might already be tracing him when he becomes infectious, when he becomes symptomatic, and then you can isolate him. So that makes in theory, Ebola quite easy to control with contact tracing. But isolation, safe burial, and contact tracing, that require a lot of resources, a lot of not only money, but also people, infrastructures. And so that's why usually they require some international intervention, or at least some big national mobilization. So that means that outbreaks can only be stopped with resources. Okay, so that's just like a brief introduction on the epidemiology of Ebola. In terms of mathematical modeling, the first model that really had an impact, and really not only at the time but even during this outbreak, was published by some people from INSERM in France, and this model is so famous that now everyone calls it the Legrand model. It's a model that was designed to understand the dynamics of Ebola epidemics. It was published, you see, in 2007, so a long time ago. And this is the kind of model that we built during the practical sessions, and the kind of model that we use on a daily manner at the London School also. So I will come back later to this model. Now I'm just going to give you a brief recap of the different things that we saw, and when we talk about mathematical modeling, what are we talking about, and how do we confront them to data. So when we talk about mathematical modeling, we talk about this kind of compartmental models. And there are different names for these models: dynamical models, mechanistic models, compartmental models, state space models. You might see a lot in the literature. It's not always obvious that they are actually the same things, more or less. The first kind of model that we saw during the practicals, and most of you are familiar with, are the deterministic model that you can describe. So this is a SIRS model, where after becoming infectious and recovering, you go back to the suitable compartment, and this is to mimic some kind of loss of immunity, due either to waning immunity of antibodies, or to... Is it getting darker and darker, or is that just me? Or for instance, some evolution of the disease, of the virus. And this is described with a set of differential equations. And you saw already that from these kind of models, you need to compute the basic reproduction number, which is the average number of secondary cases generated by a single infectious case in an otherwise fully susceptible population. And you can express R0 in terms of the parameters of your mechanistic models. So here is just the contact rate divided by the recovery rate for the simple model. And there is some results of stability analysis that tells you that there is a stable endemic equilibrium if R0 is greater than 1. So R0 is something that is probably like the big concept in mathematical epidemiology or epidemiology in general, and it depends not only on the way people get in contact with each other, but it depends also on the disease. And there is some rough, it is a rough estimate of the order of magnitude of R0 for different diseases. So for Ebola and flu, for instance, it's around 2. So this guy is going to infect 2 guys in average. For HIV, it's around 4. For smallpox, around 7. Ah, thank you. And for measles, it's quite high, it's very contagious, it's around 18. If R0 is above 1, what you will get is an exponential growth. So that's the epidemic curve over time, and that's increased exponentially at the beginning. What you want to do is to try to reduce R0 to control the epidemic. So is R0 stay above 1, is R, sorry, stay above 1. So R is the effective reproduction number, and it's R0 times the proportion of susceptible. If R is above 1, the epidemic keeps growing. If it's R equal to 1, then the epidemic plateau. And if you manage to make R below 1, the epidemic will decrease. So you see that to make R below 1, you can play on the proportion of susceptible or on the basic reproduction number. Those are 2 elements. So for instance, if you vaccinate people, you're going to play on this parameter to try to vaccinate enough people so that the effective reproduction number goes below 1. Anyway, that was deterministic models. And for the SIRS model, you get this kind of trajectory, deterministic trajectory. So for one theta, so theta is for one set of parameters, you get exactly one trajectory, x. So in the rest of the talk, when I talk about parameter, I call it theta, and when I talk about trajectories or state space, I call it x. This continuous trajectory is quite nice, it's quite convenient to simulate, it's too fast. But the thing is that life is discrete in stochastics. And actually, that's why we introduced to you also some stochastic models, where you can represent the same way as a deterministic model with the same compartments, the same transition rate, except that here we are not talking about differential equations, but about events, about transitions, and these transitions occur with some intensity, jump intensity. all Poisson processes. And we saw how to simulate this. The result is that if I simulate this kind of model, I don't obtain anymore one deterministic curve, but I obtain a lot of stochastic trajectories. And these stochastic trajectories, I have colored them in 3 different colors depending when they go extinct. So the blue one get extinct very quickly. That's early extinction, and we saw that. And for simple model, the probability to get extinct very early is 1 over R0, you might remember. Otherwise, you might have a major outbreak. The thing is that after major outbreak, the deterministic model will always go up. The thing is that in this part of the epidemic, you have very few number of people infectious. So you might break, just by chance, the chain of transmission. And that's why some trajectories here, stochastic, go to extinction. So there is no more infectious people there. But some other will go up again, because the number of susceptible there will be a replenishment of susceptible pool thanks to the transition from R to S. And so you might see another epidemic and some establishment of some endemicity. So that's the kind of differences you might see between deterministic and stochastic, which are summarized here with variability. You have a variable outcome. And you also might see extinctions. So when you want to study these two things, unfortunately, you cannot rely on simple deterministic model. You need to go to a stochastic model. Obviously, this kind of stochasticity is due to, it's called internal. It's due to the fact that we are discrete, we interact in different ways, we have some chance events at the individual levels. So we expect that the smaller the population, the bigger will be the stochastic effects. So that's why we might be interested to study this kind of, to use this kind of model for epidemics in very isolated communities, very small communities. That's quite convenient. And this is just to say that on top of any model, what we're interested in is confronting the model to the data. And so data, for us, most of the time is equal to a time series, I not YT. And when we see these patterns, usually that's where the modelers get the inspiration and try to design a model to try to understand the mechanisms underlying the dynamics that can have generated this pattern. It's not only in infectious disease, in many other morphology, you can see the same kind of inspiration. But we are in epidemiology, and so the kind of model we use have this kind of structure where you have what I presented again already is a transmission model. And this transmission model, we can describe it in general by this density, which give you the probability to observe a given state space at time t given theta. And that's usually quite easy to compute for a deterministic model because it's going to be a Dirac. But for a stochastic model, it's much more complicated. But on the top of the transmission model, you have, well, on the bottom here, we have an observation model. And the observation model tries to relay the data YT to both the model, which means to the parameter values and the trajectories generated. This observation model, usually we try to put a very simple distribution. It's what we call the likelihood, if you want. And usually we use some binomials, some Poisson or negative binomial. There are 3 very common use observation model. But just to show you about also another problem of observation, observation means also not only that we observe a fraction of the case, or maybe we observe, just a fraction of the case, but we also have the problem of reporting delay. When we observe something, we never observe something that happened at time t, we observe something that happened some time ago. So let's take the case of Ebola, for instance. In Ebola, let's say you have this number of people infected at some time t. Usually it will take 9 days before these guys become symptomatic. So this is the incubation period. And the thing is that some of them won't be symptomatic. There is always some heterogeneity in the population. Some people will be asymptomatic. But these asymptomatic guys, maybe it will take them around, like, say, 5 days, 4 or 5 days, because they seek care. This is because at the beginning the symptoms are, for instance, look like for flu, so you might not be too worried. So in average, it takes like 5 days before they reach a doctor. And again, some of them won't go to seek health care because they live too far, or they don't believe in this kind of medicine. And again, once the guy seeks health care, it might take again 4 days before it is reported to the database, just because it takes some time to transfer some thing written on a piece of paper to a computer. So you see that in total you might wait for Ebola 18 days between what you see is that and what actually happened, and you only get a fraction of all the cases. The effect of this on the epidemic curve is that if you have an epidemic that is going like this, actually with a 10-day reporting delay, you will observe that. So you have the impression in the data that the epidemic is declining. It's just because these guys, you haven't observed it yet. You observe this one, but not this one. So you always need to censor the data to make sure what you observe, at least what you have, is what actually happened. So let's say you want to estimate the proportion reported. So that was at the beginning of the Ebola outbreak. You had this kind of data kind of sensor. You don't have the decrease here. And you want to estimate you have a reproduction number equal to 2 and a 2-week serial interval. So that means that every 2 weeks you double the number of new cases. Well, if you assume that 100% of the cases are reported, you will indeed find an R0 equal to 2. And you will estimate that at the beginning you have 5 initial infected. So that's assuming that what you observe is a rarity. The thing is that if only 50% of the cases are reported, what you will actually find is that there were 10 initial infected. And when you will look at the true number, it will give you this curve here, dash point. So that means that actually your problem is much bigger. You are here. And again, if you assume that you only observe 25% of the cases, you will still get the same estimate of R0, but you will get 20 people initially infectious, and your true number is much higher. So the message here is that it's very difficult when you don't know the proportion that is reported, and you don't know the initial number of people infected. It's very difficult to estimate what is the reality, because you have a big combination of proportion of reported and initial number of cases, and that will be totally correlated, and so you won't have the possibility to estimate both precisely. But you'll be able to estimate the R0, which is independent of this. And so the first estimate of R0 for Ebola outbreak, the early analysis, were around like 2, as I showed you before. So that brings me to the motivation of inference. We saw that most of you have models and you have some parameters you don't know. That's why you were really interested into inference. There's different ways to do inference. There's a frequentist approach and the Bayesian approach. Seb already explained to you the difference. We decided to focus on the Bayesian inference. And the objective of Bayesian inference is to explore this distribution, this density, which is the probability of the model given the data. And in the model, I can separate what is parameters and what is trajectories. And usually what I do is that I marginalize to estimate either the parameters or either the trajectories, which means I try to reconstruct what happened. The trajectories, remember, is the trajectories of the model, correspond to this. is what I have no idea what it looks like. So usually we'll be interested in trying to understand what actually happened or what actually were the parameters. And so you marginalize either by integrating over all the trajectories to get the parameter, or either by integrating over the posterior distribution of the parameters to get the marginalized distribution of the trajectories. The other thing you might be interested in, and we don't talk about that, is to compare models. So you can have two models, let's say, and you want to find which model is the best. So you can use also Bayesian inference to compare the probability of a given model in comparison to the probability of another model. And you might decide which model is the best. So just to show you a bit of about the inference problem a bit more, I'm going to look at the parameter inference. That's what we have been doing. We're more interested in the lab session, and that's what the last practicals was about. That unfortunately we didn't have to finish, but you can do it. So let's have a look at the parameter the problem of parameter inference. So here you have the marginal. You have the marginal. Can you hear me well? I feel the mic. Yes, okay. You have the marginal posterior distribution of your parameter, so probability of the parameter given the data, and this is proportional to the likelihood and the prior. So theta here is a parameter, so the likelihood is the probability of the data given the parameter. This is the prior. This is the marginal likelihood, sorry. And this is the posterior. So now this I know how to compute it, is my prior belief. This is what I want to explore. So I need to compute the marginal likelihood. So let's have a look at the marginal likelihood. The marginal likelihood is the probability of the data given the parameter. And you can just expand this expression to include the trajectories x of your model. And so if you sum over all the potential trajectories of the model, then if you sum over all of this, then you will get the marginal likelihood. Okay, so that's very general. This is the case that encompasses the stochastic and deterministic approach. If you use a deterministic model, well, the probability of the trajectory given the parameters, there is only one trajectory, so there's only one solution most of the time. So you get the simplification that you have a Dirac here on the solution of your deterministic model. So then you don't need to sum anymore over all the trajectories. You need only one. So you can replace, you can simplify. And so you just need to compute the probability of the data given the only trajectories generated by your model. And that's what you do when you integrate the model with DSOL. When you do that, you compute this solution. So it's never exact. It's always a good approximation, like a Euler or Unjekuta methods. And then you can compute this because this has a closed form. It's a Poisson or negative binomial. So we just can compute it. And that's what we did this morning when we look at deep trash ops. So we can compute the posterior for a deterministic model. And that's why you can use MCMC. And that's why you have all these things at a quite standard that works quite well. Okay. So let's go back to the more general marginal likelihood, where you still have the sum over all the possible trajectories of the model. And now let's look at the stochastic case. In the stochastic case, the problem is that there is no this probability distribution is no longer known. We don't know the solution of the master equation that will give you that. So the problem is that if we want to sum over all the possible trajectories of the model, there will quickly be billions of trajectories. So that's not feasible. It will take too long. So the idea is that so for a long time we could not do inference on stochastic models. We had to use other approach or non-exact approach. And now it's possible. It's possible thanks to an algorithm called a particle filter or sequential Monte Carlo, and that allows you to get an unbiased estimate of the likelihood. And if you plug this estimate into the MCMC, then you will converge where the exact Poisson distribution. So what is the particle filter? The idea is that I cannot sum over billions of different trajectories. So what I'm going to do, I'm going to use the Monte Carlo approach. I'm going to say that I'm going to take 1,000 trajectories. And so I will sum over these 1,000 trajectories. And everything here is replaced by a trajectory, J. And so you might wonder, but how this will work? Because if I take 1,000 trajectories, how I pick them? Well, that's how the particle filter is smart, is that he managed to take trajectories that are always in the high, that are very likely, if you want. So it's an algorithm. It's beyond this talk. It allows you to efficiently get particles that have a high likelihood. So you have they contribute the most to the overall likelihood. So the objective of this is to obtain a Monte Carlo approximation, and this can be done using a particle filter. So in this case, we cannot really compute, but we can estimate. And if we can estimate, it will work. So we have an estimate, if you want, of the posterior density. Okay, so we didn't see the stochastic part in the practicals. It's beyond the practicals, but if you're interested in that, you need to find keyword particle filter sequential Monte Carlo. It's quite a heavy literature, but some papers are quite accessible.
What's the difference between this and standard importance sampling?
So it's a kind of importance sampling, but here is sequential. So you do that at so you have your time series, and you propagate your particles. So they will start at time 0. You will simulate the model, and then you will reweight your particles at the first observation time. If particles have a high likelihood, they will be more likely to be resampled at the next time step. And so that's why you kind of like always keep the good trajectories. But I mean, there is some more theoretical justification what I'm saying now, but it's a kind of important sampling. So now we have an estimate. We can compute or we can estimate the Poisson distribution. What we want to do, because we can compute the Poisson distribution for a given theta. Now what we're interested in is to sample from this Poisson distribution to find all the theta that are within the distribution. So that's why we use Markov chain Monte Carlo, MCMC, to sample from the marginal Poisson distribution of the parameter. And here again, we kind of didn't have, well, we had some theoretical justification by Seb yesterday of the principle of the algorithm. The very basic idea is that imagine that you have only 2 parameters in your model, theta 1 and theta 2. And let's say that this is your target. This is the Poisson distribution. So here it looks nice, but it might not look like this all the time. It might not be unimodal. And so you want to explore this distribution, and you have no idea how to do that. Well, you use MCMC. So let's say you initialize your algorithm here, so quite far from the target. The idea is that you're going to use a proposal distribution. So proposal is a different distribution. Is that, for instance, a Gaussian distribution with some covariance matrix. And the size of the covariance matrix is going to tell you how far you explore around your first data point, your first parameter that you have chosen. So let's say you propose this theta star parameter here. Well, you will decide whether you accept it with some acceptance ratio. So the acceptance ratio is made such a way that by accepting, rejecting, at some point you will build a Markov chain, and this Markov chain will converge to a stationary distribution, and this stationary distribution will look like this one. So you accept, reject, and you repeat. Let's say I've accepted this one, I repeat, I propose a round, and I accept, reject, and at some point I will reach the, not necessarily the mode, but at least I will reach the high posterior density. And I'm not interested in getting the highest part of the mode of the distribution. What I'm interested in exploring all this. And that's what the Markov chain, Monte-Carlo Markov chain property is that if you explore long enough, you will explore all the posterior distribution. So you see here, I have my chain that jump from one part to another of the parameter space, but when I look at the histogram of the path, I will get the distribution. So the Markov chain in the parameter space is generating samples that approximate the posterior distribution. All right? So I will give you like just a recap of the thing that you have seen, and that's really the fitting that we were interested in during the Ebola outbreak, because we had few data, but it was still data, and so we were interested in trying to estimate the parameter like R0, but also some other. So after this very long digression, I come back to the Legrand model, which is, remember, the model, the first model that was become famous to to study Ebola epidemics. And just before I go into the model, so just a quick description of the model, of the structure. It's based on a ACIR model, but it's a bit different. So initially, people are susceptible. Upon infections, it goes through the exposed class, and then they become infectious when they become symptomatic. And then they have the choice between three possibilities. Either they recover, either they die, or either they go to the hospital. So they recover at home, they die at home, or they go to the hospital to seek healthcare. When they are here, they have at the hospital, they have two possibilities: either they recover or either they die. But when the die is not finished, because I told you that funeral transmission happens, so we're going to consider these guys until they are buried. When they are buried, we can safely ignore them. So in this model, it's a bit different than the model you've seen until now. You have three infectious compartments, I, H, and D. I for people infectious in the community, H for people infectious in the hospital, and D for people that are dead but not yet buried, so the body are still infectious, so it can still transmit. If you look, I didn't put the transition here, but there is transitions, parameters. If I look at the reproduction number for this model, I can actually split it in three components that correspond to my three infectious compartments. So here R0 is equal to this kind of big ugly expression, but this one corresponds to the reproduction number of people infectious in the community. This one corresponds to the reproduction number of people infectious in the hospital, and this one of the people that are dead but not yet buried, and that can transmit during the funeral. So you see, you can separate in three parts. The problem is that when you fit, so that's the kind of model you might want to design because you know about the epidemiology of Ebola. So you think this model is realistic. It's a good description of the epidemiology of Ebola. The problem is that you only have access to this kind of data. So they had access to the outbreak in DRC from 1995 and another outbreak in Uganda in 2000. And both ways, they only have access to the overall curve, so the overall number of infectious, the number of cases over time. So that's the kind of data that usually you can find on internet. It's just number of cases reported over time. So you see you have two epidemics, looks roughly the same in terms of the highest incidence, in terms of duration also. And here is the fit of their model, and you see that, okay, it's a decent fit. So, and then you are interested in the parameters. So you fit your model, you look at in the data, you look at the parameters, and so here you have the parameters for DRC and here for Uganda. And what you are mostly interested in is in the basic reproduction number. So here, basic reproduction number is 2.7, and it's exactly the same for Uganda. Not that surprising because the epidemic curve looks very similar. However, if you split into the different components, so the community, hospital, and funeral component, you see that you have different estimates. In DRC, the estimate was mostly the funeral component that was important, where in Uganda, it was mostly the community component. So, and you see like, so overall like very similar outbreak, but very different estimate of the different components. So here you might agree or you might disagree with what I'm saying. And actually, you should disagree. Because if you look at the second part of the estimate, this is confidence intervals. It means that how confident I am with this estimate. And if you look at the confidence intervals, and you look at the lower bound and the upper bound, you see that they are quite wide, and they span 1. That means that, for instance, if I look at here, the hospital component, my point estimate is 0.01, but it could be between 0 and 3.5. And that's a different story if it's 3.5 than if it's 0.01. Because then you might not close the hospital, you might close it. It's a very different story. So that tells you the story that the lesson from this is that it's a good model, it's more precise than what we had before. But unfortunately, with this kind of data, there is no way you're going to be able to really estimate precisely the different components of R0. You might have a good estimate of the overall R0, you see, it's clearly above 1, here and here. But you will not be able to estimate the subcomponent. So don't be too ambitious with the model. If fitting is not magic, it really depends on the data you have. Yes?
Why do you need a D component in that? You didn't have to.
So why do we need this guy?
Yeah, why do you need the exposed component if you just had SI?
Because it's 9 days. It's around 10 days. So clearly you're gonna it's not negligible. All right. So when we started to look at Ebola, that was the first paper we probably read about modeling of Ebola. And we were in July 2014, and we were at the London School of Hygiene and Tropical Medicine. And the director of the London School of Hygiene and Tropical Medicine, Peter Pyatt, is also one of the scientists that went in 1976 in DRC when the first outbreak of Ebola was reported. When the Ebola outbreak was becoming more and more present in the media, and we heard about it, we went to visit him in his office, and he told us that actually he still had some archives on the 1976 outbreak that he never really published or never showed to anyone. So we went into this archives and we found some data, and it's how we get a head start into the modeling of Ebola outbreak. So I'm going to tell you a bit more about that in the last part of this talk. But just to give you a bit of context, so this first outbreak in 1976, it happened right here in Democratic Republic of Congo. If I zoom in, you see it's the forest, and this is the Congo River. And if I zoom in again, this village here called Yambuku is next to this river here, which is called the Ebola River. And that's where the Ebola virus takes its name from. So that's where the first time that Ebola was reported was here. It was in Yambuku. Yambuku looks like this at the time. It's a typical rural village where you have like one main road and some farms and houses. And in this village, there was only one hospital. It was a mission hospital that where some Belgian nurses, Belgian sister, actually, they were half nurses, half sister, I guess, were working. And that's where the first Ebola cases presented to this hospital. Very poor hospital with no surgery, nothing like this. It was mainly an hospital where they were giving like some basic health care, some vitamins, for instance, stuff like this. And when the first Ebola cases arrived, they realized that after this guy, there were a lot of other cases, and it was a new kind of hemorrhagic fever, very deadly, and they never saw that before. So what they did is that they took a sample of the blood of one case, and they shipped it by plane to Belgium, where Peter Payot was working in a virological lab. And when they look in the microscope, so that's Peter Payot, they found this, so a very special virus, very long, very like a big string, and they never saw that before. So they were not sure, so it looked a bit more like another virus called Marburg. And because at this time there was not possible to do sequencing, so they sent it to the CDC in Atlanta, so they can really like identify whether it was a new virus or not. And when the answer came, it was yes, it's a new virus, and it has never been observed before. So they decided to send, because the situation in Yambuku was getting worse and worse, there was a lot of cases, they decided to send some international team. And so that's part of the team, and that's again Peter Payot. And there's some nurses that didn't die. There was a lot of deaths among the nurses. And so the team arrived, and they started to do some investigation to understand what happened. And when they did the investigation, they noticed two things. The first thing is that it was mostly young women between 20 and 30 in the age of being pregnant that got the disease. And the second thing is that they figured out that the further you were going away from the hospital, the less cases you have. So the hospital seems to be the epicenter. So this was a clear sign that there was something kind of like not natural here, because there was a bias toward a certain age group and a sex ratio also unbalanced. And so what they figured out quickly is that in this hospital where the first Ebola cases went, they were reusing syringes every day because they didn't have enough syringes for everyone. So there was only 5 syringes that were reused every day. And obviously that led to the quick propagation of the virus through a nosocomial infection. So when they did the investigation, and what we found in the archives of the library of Peter Payot is this kind of data. So this is called a line list, and it's much more detailed than the data that usually we use in modeling, which are just time series. This is actually, for every line, you have a case. For every line is a different person, and you have a lot of information on every column. So for instance, you have the age of the person, you have the sex of the person, you have when the disease onset and disease ended, And you also know whether the person die or recover. So you see how deadly is Ebola. And you have also some extra information on the family and many things. But very importantly, and that was the first time we were seeing this kind of data for Ebola, was these 4 columns that correspond to transmission. So that was the information on the route of transmission. And there was 2 main routes of transmission. Either you got Ebola through a person-to-person contact. So they were asking to every case, did he have contact with someone who is also a non-cases? Or SYR, which means syringes. So all these guys, they got a syringe injection with probably a contaminated syringe. And you have the case where you might have both, or the last one is other route of transmission, and this was mainly when you have like some baby died because there were a lot of pregnant women, so it's miscarriage. Okay, so very important these 4 columns because we have the route of transmission. And now if I look at the time series, which is like this, and I map the route of transmission on the time series, I can see that at the beginning of the outbreak is mainly syringe contamination that happened, whereas in the second part and in the last part, it's mainly person-to-person. So here you get an extra information that you would never get if you don't have the route of transmission. These dot lines correspond to the time when they close the hospital. So when you look at this time series, you might think that, okay, well, it seems that they closed the hospital, and after that, there is much less syringe transmission. So this probably is the reason why the epidemic decreased. But this is a kind of hypothesis that you want to test with the model. So you can build a model and test this hypothesis, trying to look at actually what happened during this outbreak. What did happen in terms of transmission? When the transmission stopped? Was it linked to some intervention or not? That's really important. So what we did is that we took Legrand model here, same model as Legrand, because we had some hospital transmission, it was nosocomial. We had some also people dying and some people in the community. And we started to try to estimate all the parameters. We quickly realized that it was not possible. In the same way as in Legrand papers, they were not able to obtain precise estimates for all the parameters, for all the reproduction numbers. It was not possible here neither, just because we only had information on person-to-person contact, but we didn't have information whether this contact happened in the community or during the funeral. So if you do the same things as in Legrand, that means that you try to estimate all the parameters here, and you look at the posterior distribution of the reproduction number in the community and the reproduction number in the funeral, what you get is this big spot that span both above 1 for both parameters, which means that you don't know whether it's most likely to be here, but it could be that a lot of funeral transmission and little community, or the opposite, or something in the middle. So it's not possible to disentangle these 2 ones. Again, I just insist on this because when you will do your fitting, it's not because you find one parameter set that give a good fit, that there is no other combination of the parameter that give also a good fit. And so you should be careful if it's the case in interpreting your estimate, always to consider the confidence that you have on your estimates. Anyway, so what we did is that we grouped these two estimates into a single estimate because they were correlated, and we call it the person-to-person reproduction number. On the opposite, the syringe, the hospital transmission was separate, so it was possible to estimate it precisely. So let's have a look at those estimates. So the reproduction number at the beginning of the outbreak was, the median estimate was above 3 for hospital transmission and above 1 for person-to-person. And when we look at credible intervals, you see that, well, we are highly confident that this was quite high, and we are also highly confident that this was above 1. There is a little uncertainty here, but roughly most of the mass of the Poisson distribution is above 1. And overall, with just both of them, you see that it was quite high. This is quite high as a reproduction number, and this is because a big contribution of hospital because of the syringes. You can measure that here. Which was quite new here is that actually the person-to-person transmission was sustained. Before that, we were mostly thinking that Ebola is not clear whether it could spread in the community because all the previous outbreaks were linked to some hospital transmission. What this data, very detailed data, show you is that actually you can separate both routes of transmission, and you can see that even if you close the hospital quickly, you can have some sustained transmission in the community just because it's above 1. All right, so that's just what happened at the start of the outbreak. Obviously, we're also interested in what happened as the outbreak expands. And so to do that, we had to use some time-varying beta. So beta, the contact rate, we have to imagine that this thing is going to change over time. The reason if you don't do that, that means that you just expect the outbreak to finish just due to depletion of susceptible. And we know that for the Ebola outbreak, it was not the case. You don't expect that you don't have any more people in the community for the epidemic to stop. So we have to imagine that it's probably like something that changed in the contact rate between individuals. And so I'm going to say that my beta at time t is just a beta at time 0 times some function of the time and some parameters. And I'm going to use something quite flexible but still parametric. I'm going to use a sigmoid. So the sigmoid, it can be quite steep or it can be go slower. So I'm going to assume that it decreases, but I'm going to try to estimate the shape of this sigmoid. And that's possible also. That's extra parameters in the model, but you can estimate them. And I'm going to show you this estimate. So this is my two sigmoids for the hospital transmission and the person-to-person. And this is overall. So you see that overall you start above 4, as I showed before, and then you quickly drop here around like September 15, but you're still above 1, so you're not yet under control. And then after this time, you go below 1 and you go to 0. So that's the reproduction number of the hospital that contribute to this big first drop, and then the person-to-person contact that decrease over time contribute to decreasing the reproduction number person to person. So this happened at a slower path and is smoother. So the question when you see that is that, well, the hospital closed here, the dots. So you see that the reproduction number in the hospital drops much before. So you might see that this might suggest that the hospital closure didn't play such a big role. We went into some other studies that were made at this time, trying to describe the outbreak. And what we found is that actually, quickly after the beginning of the outbreak, people started to associate the hospital with death. They had no idea there was a virus, there was probably few knowledge about transmission of infectious disease, but they quickly associated the hospital to death, and so they stopped going to the hospital. If you stop going to the hospital, well, you stop the nosocomial transmission, and so that the model suggests that this drop was quite quick, quite sharp. However, the people were still transmitting in the community because the hospital already spread the disease in the community. So there were people like infected in the community. And this took a bit longer to control. But again, it seems that this was due to some natural change in behavior. And for instance, people at the end of the outbreak were not using the traditional burial anymore. By themselves, they also associated traditional burial with a lot of Ebola cases after. So that means that for Ebola, the change of behavior is really important, and this can happen before any intervention. just because it's so deadly, it's such a big impact on communities, that communities will change by themselves. All right, so that's just to show you a bit of fit. The solid was generated with a theta. So if you want to use a theta, you can generate this kind of plot. So the dots here are the data, and we have different data sources. I didn't explain this, but we just split the time series in 4 components for the dead, the new cases, for instance. And this is just because we fitted with a deterministic model, because it was simpler, it was quicker. So we fit it with a deterministic model, but then it's good to validate with a stochastic one. So you fit with a deterministic, you sample some parameter from the posterior distribution, and then you fit some stochastic, the same model, but the stochastic version, and I show you that for every stochastic model you have a deterministic one. And then you look at the trajectories. And what we found is that most of the time the trajectories were looking like what actually happened in the data, but some trajectories were incredibly high. And that's just because by chance, you might have, because you have such a big population number at the beginning, you might have sparkled actually a much bigger outbreak. And so that's what we computed. So that's the model that we fitted. And you see that when you resimulate, you can get outbreak much bigger, like higher than 1,000 cases. And then we tried different things. If you close the hospital, if you close the hospital before, or if you reduce the person-to-person transmission, and you see that this has some effect, so you can test with your model which intervention will be the best. So here, clearly closing the hospital early would have been a better solution. And then we also comparing to the previous outbreaks, and it was kind of the same order, all these plots. Anyway, so just to summarize this work, we could figure out that the mission hospital, while it catalyzed the epidemic and was rapidly associated with Ebola by villagers, and that's why the reproduction number decreased quite quickly. However, the reproduction number in the community was still above 1, and that's why the outbreak keep going on even after the change in hospital consultation. And so this also essential. Controlling in the community is essential to control the outbreak, and that was one of the lessons at the beginning of the Ebola outbreak. There were also some potential for larger outbreak that we found with resimulating. And again, in terms of data, we really found that it was key to identify the route of transmission, and that would have been possible without a precise epidemiological investigation. We won't be able to tear these 2 routes of transmission apart just with the model. So, okay, so I'm done with Yambuku. I'm done with the recap. In terms of time, how are we? Another 20 minutes? Okay, so, yes?
Are they drawn from a probability distribution, or are they again just single numbers?
Okay, so at this time we had very few estimates, but we had estimates from the line list. So what we did is that using the line list, we could compute, for instance, the duration of the symptoms. We also have some information on the incubation period, because we had information on when the people got the contact with the suspect index. And so using that, we actually we used the median estimate to fix the average incubation period, for instance. We could have used the distribution to, actually I think we did that. I don't know if we fixed it or if we took the empirical estimate from the line list as a prior distribution, because we could have done that also because it's a Bayesian approach. But so the idea is, is to use the line list, use information at the individual level to get some estimate of some parameters, constrain these parameters during the inference, either by fixing it or using a strong prior. And then during the inference, we really focus on estimating the reproduction number, for instance. So that's the approach we took. So it's kind of like reusing the same data, if you want, but because they lie at different levels, it means we have the time series where we fit the model, and we have the line list that we use to take the parameters. So it's kind of like it's not fully Bayesian, but it's kind of acceptable. Does that make sense? Yeah. So you mean the delay in the reporting? Yeah. So so what I showed before with the 18 days. So in this model, because it's mechanistic, we implicitly account for for instance, the first part, which is just for the exposure, which is 9 days. The thing is that usually what we observe in the data, so for instance during the Ebola outbreak, we have a report date. But with the line list, we had onset dates. So actually the only delay that we had in the model was just the exposed period, the latent period.
So that's because it was in a hospital setting?
No, that's because it was epidemiological investigation, and so they went door to door and they asked people, when did you have first symptoms?
I see.
Obviously, if you have everything is in a hospital setting, we'll have very detailed data. But the outbreak was not just in the hospital, it was also in the community. It was initiated in the hospital, but not all the cases went to the hospital or went to seek treatment at the hospital. Yeah. All right, so let's go back to the outbreak in West Africa. We are 22nd of March. We are just here. And over the next few months after the WHO officially declared the outbreak, I don't know what was on the news, but there were probably many other things, because there were very few attention actually. But meanwhile, the outbreak was spreading very quickly. And actually during this time, it started to reach the capital of the three main countries, Guinea, Sierra Leone, and Liberia. So that on the 8th of August 2014, the WHO declared the outbreak world emergency. So at this time, you could not ignore it anymore. There was already some people working here, like MSF, the CDC also was there, but clearly there was a lack of international intervention. So that's the time series of across all Africa, of West Africa. But this actually doesn't give you the best picture of what is happening. To do that, you need to split between the different countries, Guinea, Liberia, and Sierra Leone. And you were seeing at this time that the dynamic was already quite different. In Guinea, there was this kind of waves. The thing was waving. Where in Liberia and Sierra Leone, it was clearly an exponential increase, expansion. It was getting really fast, really, really quickly. So that over the next months after that, so until the end of the year, actually we saw a big increase in Liberia, followed by a big increase in Sierra Leone, but also very surprisingly a big decrease suddenly after in Liberia. So that was quite unexpected. There was a lot of people at this time that didn't really believe that this was happening. They just saw that people stopped going to the hospital to report. So they were staying in the community and dying secretly. But at some point when you see the number of cases decrease, well, it was actually a real fact, because you cannot hide thousands of people. So, so that was the outbreak in Liberia. The Sierra Leone one, by the beginning of January 2015, was following kind of the same trend, but you see that it's quite unclear if it's the peak or not here. And in Guinea, it was still special. It was kind of like quite flat with some special waves here. So very different dynamics. And what was done at this time, at the beginning of this period, obviously here, is that given the rate at which we were increasing, there were some models that were done. There were some models trying to estimate the reproduction number, and this model also they tried to forecast what could happen. Obviously, they didn't find this, but they had a big impact nonetheless. So probably the model that had the biggest impact was developed by the CDC in Atlanta and published in this report of the CDC. Was they tried to estimate the future number of cases of Ebola in Liberia and Sierra Leone. So they didn't do Guinea because Guinea, you saw, is just quite difficult to fit, you can imagine, with all these ways. But looking at Sierra Leone and Liberia, they fitted a simple model. Well, not that simple actually, but they fitted a model and they look at the reproduction number and then they make a forecast with the same reproduction number, assuming that nothing changed. And the projection were all over in the media the next day because they were saying that, the model showed that you might expect 1.4 million infected cases by January 2015. So we are moving to something with probably something like 60, 50, 60, 70 cases per week to 1.4 million. So that got a big attention in the media. This is actually not very complicated to find these results. It's just because given the reproduction number that you find, if you just, with a doubling day of around 15, 20 days or 13, 40 days in Sierra Leone, we quickly arrive to very big numbers by the end of the year. So at this time, in terms of impact, that was probably quite huge. It was not the only impact, and there was many, many other things. There was also at the time when the first case arrived to the US. At the same time, there was the first case imported in Nigeria, the most populated country in Africa. So all these things were worrying the international community, and they knew that they had to do something. But in terms of modeling, that's probably the one that got the most attention. The thing is that, as I'll show you after, the epidemic declined quickly, and so quickly, this guy had some journalists on his door asking why your model show 1.4 million when there is 65 less cases actually. So obviously it's because, as I told you, there was some basic assumption behind this model, nothing changed. And when you show a forecast, you need to be very cautious. You don't need just to summarize this with only one line in the news. Otherwise, you misinterpret what is all about this projection. But nonetheless, Martin Melzer, he had was on the spot for some time after that, which is not, I guess, a nice thing. But so you can also think about it on the short term, maybe his projection, catastrophic, had some great impact to mobilize the international community, but on the long term, maybe it has a bad impact because people tend to think that models are wrong or just imprecise or whatever. And it was partly also because he was a bit unlucky. So if you go back to when he made the predictions, and you look at, so this is the time series in Liberia on the first two panels and Sierra Leone. And this is on the right side, this is the data that he used. This is the data that was available at this time. And this is the data that are available now. So that's actually what the epidemic was kind of looking like more. And that's the data we had. You see that are much more noisy, but kind of the same trend. And this shaded area, what it corresponds? It corresponds to, so the beginning is the data. So when he fitted his model, he fitted up to this time. And this time is the time between the moment he fit, the last data point he fit, and the moment the paper was published. So you see that this period of 1 month was quite key for the Liberia dynamics, because that's when they turned on the epidemic after such a big increase. And this was kind of not that very obvious in the official data that we could find this time, but clearly he really published his paper at the moment where it was just after the exponential increase for Liberia. For Sierra Leone, it was still increasing, so we had to wait a bit after. But that shows you also that publishing in real time is really challenging, especially for diseases like Ebola that evolve very quickly. Anyway, another problem that I wanted to show you, just because it's a good thing to see that even at CDC they sometimes do some very simplistic fitting, is that when you look at their model and you look in detail at the parameter estimates, you don't see any confidence interval. It's all point estimate. There is no confidence intervals. And actually, when you look in detail at the model, you realize that they do a bit like in the Legrand model. You remember, with the 3 infectious compartments, community, hospital, and funeral, they use a similar model that was fitted to this kind of data. The problem with that, well, you know it, is that you cannot really estimate precisely any of the parameters. And actually, so that's their estimate, 0.02, 0.03, 0.3, 1 digit. And what they explain is that the value were used to obtain a good fit of case estimated by the model to the reported cumulative cases. So then you have to dig a bit deeper in the paper to find how they fit. But indeed, if you look at the fit, so what they fit is the cumulative cases. So that's why it's increasing. And that's the model, that's the data. And okay, you say, okay, it looks a decent fit. I will tell you later that you should never fit cumulative incidents. But if you look at the methods they use to do the fitting, they don't use MCMCs, they don't use some kind of like optimization software. They just use some grammar recipes, you know, like so they have like 3 parameters, and the 3 parameters were altered until the estimates of cases for either Sierra Leone or Liberia produced by the model fit the reported case to date. Visual inspection was used to validate the fit. So that's the kind of thing that everyone can. Yes?
What was the R0 value that they found?
The
R0 value?
R0 was around 2, something like this.
That is correct, right? That estimate is right. It's just
That is correct. Yeah. What is not clear is that this could be any combination of these three reproduction number: community, hospital, funerals. So because you have an exponential curve, so you could fit just an exponential and get the reproduction number. The problem is that you say that I have a very detailed model and I can estimate the contribution of hospital, community, and
correct. So the mistake made is to underestimate the effect of interventions at the community or hospital level. Is that what?
Well,
why it turned around?
The risk, yeah, is that if you look at their estimate, it's mostly in the community, and then there is timeless risk for. This is roughly funeral, and this is hospitalization in the hospital. So you might think that, okay, we need to target community. And maybe that was right. But they could have obtained like a different estimate. They could have obtained like something saying that you can get actually much more funeral transmission. So I'm not just saying that scientifically, it's not objective. They could have obtained different estimates, and from different estimates they could have like advise different intervention. So they probably either they knew that they had to target the community, and that's why they kind of like keep this estimate quite high, and the other one less important, or either we don't know exactly what.
No, I agree with that at a scientific level.
Mm-hmm.
My question was that the leveling off, is that something to do with the natural history of Ebola, something changed in the virus, something mutated, or is it just the fact that it was a bad estimate given the data of the initial number of cases?
For the R0?
Yeah, I mean, if you said the R0 is roughly correct, right?
Yes.
The total R0, how it's divided is wrong,
yeah.
But the total R0 is roughly right. But then this sort of completely unrealistic estimate of the total number of cases.
The forecast.
Yeah, the forecast. Was that because something changed with the virus?
So that was the big surprise. Is why so you do your forecast. So you just keep going with the same reproduction number, And by January, you obtain 1.4 million. So what happened? Why did we observe a decrease in the incidence? And there was a combination of many things. Combination of change in behavior of people, combination of intervention. The intervention started at roughly at the time where the number of cases started to decrease. So that was probably the two main reasons. We didn't have the vaccine at this time, so it could not be the reasons. But clearly, making a forecast assuming that nothing changed is very simplistic because you expect.
They also made a forecast assuming that 70% of cases will be isolated.
Yeah, true.
And that number was much closer to the.
So yeah, so you do a forecast based on some assumption. So there was this forecast that was nothing changed, and then you can say, okay, if I have an intervention, that will happen. But actually, it's more like scenario than forecast. So it's not like a way.
My question was, did it have anything to do with the natural history of Ebola, or was it only intervention? What's known?
Yeah, we don't think so because we don't think so because the genetically the virus hasn't changed much. So we think that there's no evidence really for any significant change.
So that was the forecast with and without intervention. So clearly here, the no intervention and the intervention. But I mean, that was not in the media, I guess. Another lesson for you guys, for the students of the lab sessions, is there was some people in the modeling community that argue that fitting cumulative cases, and this was done by most of the first modeling paper, was not the right thing to do. And so to show that, they did some fitting to show what happened when you fit cumulative versus when you fit incidence. And the problem with cumulative is that you propagate the error. So if your data has a big mistake at some point, well, you will find this mistake later on because it's cumulative. So it's always better to fit raw data, incidence data. And so here is just, so it's a paper by Aaron King and published at the same time as the other paper we published on, so there was kind of like a little battle in the community. It's quite nice. And where you can see that, again, like here is a simple forecast, nothing changed. But when you forecast with a stochastic model, fitted on raw incidence, you have much bigger variability than when you fit with a deterministic model. You forecast a deterministic model that was fitted on a cumulative incidence. So again, same raw data, but different way to present this data, cumulative versus just incidence, and different type of model, stochastic, deterministic. So obviously with a stochastic model, you have such a big range of estimate that the 1.4 million estimate would have been actually would have come with a very wide credible intervals. Nonetheless, all the first paper that we saw, including papers in Science, were fitting cumulative incidence, and it's very difficult to understand what happened in the cumulative incidence curve. So here, for instance, you have the forecast, and you have so the shaded area is the model forecast. It was fitted up to this point, the red point, and that's all the later data that was included in the final paper. And it's very difficult, but you see already that here you seems to be in the kind of the inflection point almost, and obviously it's not what this model says. But if you were showing the incidence curve, it will look very different. You will clearly see that it's not a good fit. And that's because, so again, I took this paper and I look at the different point, the point where they fitted the last data point, and the point where they publish. So you see there is a lot of time, there is almost like 3 months, 4 months. And on the cumulative, where you see this thing is kind of similar to that. And well, okay, the fit looks nice on the cumulative, But clearly, in terms of the weekly incidence, you already have big decrease of the incidence. You are here, and your model predicts something that still goes up. So be very careful with when you see cumulative incidence. Okay, so I think maybe 5 minutes to conclude that. Just to tell you that, well, after this part in January, the epidemic really declined, and that was in all 3 countries. Liberia was the first one to be declared Ebola-free. But since then, it has been some problem with some recurrence of disease. And well, I don't have time to go through what we did in terms of modeling, but we tried to look at some deeper level, at the final resolution, looking at the different districts of West Africa. And when you look at the data on all these districts, you actually find that the dynamic sometimes is very different. So this is, for instance, all the district of Guinea, and you see that. So the epidemic started in Gekedu. That's where the small village I show you is, and then you have sporadic outbreak a bit everywhere, and you see they look mostly like waves or single outbreak here, and you have some district where you have big outbreak like here. So that's typical of a super spreading event, or like it was 2 cases that lead to 2 unsafe burials that generated 80 cases. That was the situation in Liberia, where it's a bit different. Now you have like a big epidemic in Montserrado, which contains the capital, Monrovia, and more sporadic outbreak in the other districts. So I tell you also that geographical, spatial geographical specialization is really important. And in Sierra Leone, it's a bit like in Liberia. You have a big outbreak in western area, which contains the capital Freetown, and some smaller outbreak everywhere else. So during the epidemic, we focused on western area at some point because there was so the UK response, the UK help was mainly focused to Sierra Leone and to Freetown because there was the biggest outbreak. So we got in contact with some people from MSF on the field that were trying to wonder how many beds they should open over the next few weeks to treat all the cases. And to do that, we use a very simple model, SCIR. There is no more hospital, community, and funeral transmission because we won't be able to estimate all this. And we just, with this minimal model, we account for 3 sources of stochasticity: demographic, I told you before, observation also, I told you before. And now also in the transmission, we're going to assume that transmission is a stochastic parameter, and we use a diffusion for the transmission. And I'm not going into detail, but it just means that you can make the transmission change over time, and you want to infer this variation. We use it some library, so not FITA, but another one called SSM. It's called in C. And just to show you the 1.4 million estimate, what happened when you do that in a fully stochastic way. So that's western area. The very beginning in August 2014, and that's the number of cases reported every week. That increase over time, you can see. And that's my median fit of my model, and that's my median reproduction number that decrease over time already. So go from 2 point something to a bit below 2. And that's my threshold at 1. And so this is because I have a time-varying reproduction number. It's a diffusion, and I estimate the path of the diffusion. So what happened after that is that I can do a forecast. I can say that nothing changed from this point. So I'm going to use the same reproduction number from now to January, and that will give me this curve. And that's roughly corresponding to the 1.4 million estimate of the CDC. The thing is that because I use a Bayesian approach, I can also obtain some credible intervals on my parameters. And so that's my 5% credible intervals. And you see already that you have a big range. It's very difficult to see, but so I go up to 10%, 15, 20, 25, 30, 35, and I go up like this until 95. And I have a big variability on the estimate of R naught. Obviously, it's concentrated over this value, but if you go to 95% credible interval, it's quite high. If I look at the interquartile, it's quite concentrated, but already this variability, when you propagate over several months, it gives you this range of possible trajectory. And I cut here because it could be much higher. And this estimate, so you see that what the point of having this estimate when you have such variability. So obviously, when you look at the data, well, they were within the credible intervals. So, or probably we could have said to the journalist that our estimates were right. But I mean, it's just confidence based on uncertainty here. There is nothing in the model that really tells that the reproduction number drop over time, and that's why we had this epidemic curve. Okay, so I'm going to stop here, and so thank you for listening, and yeah, I hope that you got some better example of what model can do and what it cannot do, and how fitting should be. Well, you should always be careful when you do some estimates. Thank you.
Question?
I think you already had too many questions, Gautam.
Okay, so I had a question.
That's
normally when you think about property distributions, fitting the cumulative is usually a better idea than fitting the derivative of that, which is the distribution itself, because it's smoother. And
yeah, but
it's just one is an integral of the other thing.
Yeah, it's always smoother.
And so normally the instruction would be that if you want to reproduce or find a property distribution, you should always work with the integrated version, the cumulative version, rather than the differentiated
But
one.
that's for a distribution when you have independent sample.
Yeah.
Where here, actually the data are not that independent. But we assume that it's not part of a distribution of data. It's an epidemic, so there is some autocorrelation. So in this case, that's why you have the propagation of error. In your case, you won't expect that the sample you get.
That's true. Yeah.
So that's because of the time dependency.
So I guess, I guess the other reason is that if there is an intervention, it will shift the curve up or down, but it will not change the derivative, but will change the integrated value. I guess that's another reason.
Yes, so your cumulative might just plateau earlier if the intervention, and in the incidence you will see like a drop.
Yeah.
It's just like, as human beings, we are very bad at computing derivative just with your brain, so it's probably simpler to show the incidence than dealing with cumulative.
Okay. There are no more questions? Then let's take a break for coffee and come back by 4. Thanks, Sebastian. Thank Anton again.
Thank you.